presentation for the AE 4610 final project, Resistive Coil Heater Modeling and Control by Jason Smith and Katie Wires. Here's the problem setup. We're given an input temperature and set a desired output temperature. The output temperature is fed back to the coil and it adjusts voltage until the steady state output is achieved. And you can see our box heater schematic here on the slide. The box heater model was derived from thermodynamic and heat transfer equations. The first equation shows the relationship between output temperature, temperature change in the system, mass flow, and heat addition. For our model, we keep the initial temperature constant to model, for example, stagnant outside air coming into a home. The specific heat and mass flow are related to the thermal resistance, so this can also be simplified. This gives the final equation that can be rearranged to find the open loop transfer function, also known as the plant for our system. Here's the Simulink model used for the experiment. With a given input temperature and desired output temperature, the PID controller shown adjusts the change in temperature needed to reach the desired output and applies the correct amount of voltage to do so. The scopes show the voltage and coil output temperature response. Here you can see the desired performance parameters of the system. Percent overshoot of 1%, steady state error of 1 Kelvin, and time to peak of 1 minute. The damping ratio can be found from the percent overshoot, and the natural frequency is found from the peak time requirement. We calculated a damping ratio of 0.826 and a natural frequency of 0.0929. These values are used later in the gain definition equations. This slide shows the addition of PID control onto the open loop transfer function and the derivation of the closed loop transfer function. The closed loop transfer function is then compared to the standard second order transfer function. By equating the S and constant terms of the characteristic equation to the standard transfer function, the gain equations are derived and shown here on the right.
Now we will move into the results section. Here is the voltage and temperature response for a PD control scheme. This was implemented by simply setting Ki, or the integral gain, equal to 0 and solving for the remaining gains. The temperature is steady at 289.5 Kelvin and the voltage at 1.5 volts in its steady state configuration. All performance parameters were met besides steady state error. This run confirmed the need for integral control on the system. Here we implemented the PID controller. We started with initial gains of 1 to understand the system behavior on a surface level and understand how they should change from this baseline. The steady state error is corrected to 0 and the time to peak meets the design criteria. However, the percent overshoot is too high. Also, the voltage response shows that the system is saturated at 120 volts, which is not ideal. These issues directed us to tune both the integral gain and the proportional gain and follow the gain equations derived earlier in this presentation. Here is the voltage and temperature response for the tuned PID controller. All performance criteria were met and the voltage is no longer saturated. The steady state error and the percent overshoot are well below the criteria, and the time to peak has great margin as well. Here is a summary of the cases tested, the gains used, and whether or not the performance criteria were met. Some relationships we can identify are the integral control gain's ability to eliminate steady state error. We can also see the integral gain and proportional gain's ability to decrease rise time but increase overshoot. These characteristics display the trade-offs that come with designing and tuning a P and ID controller. From our experiment, we developed quite a few conclusions and findings. We modeled a real-world heating device, demonstrated a working P and ID controller, and we saw the direct effects of changing integral, proportional, and derivative control gains. We also correctly derived those gains to meet performance criteria and tuned them accordingly.